Okay, so first of all, in all of these, what's my nucleophile?
The left one.
The left one, and specifically, right, that alpha carbon. The chapter is called alpha carbon chemistry. It's because that alpha carbon is going to be playing the role of the nucleophile. Why can that alpha carbon play the role of the nucleophile? What's so special about that alpha carbon? It's not even actually the alpha carbon that's so special, it's that alpha hydrogen. What's so special about that alpha hydrogen?
It's acidic.
It's acidic, right? So it can actually be removed fairly easily. So that's the basis of all this alpha carbon chemistry, is that alpha carbon, meaning the one right next to the carbonyl carbon, you can pluck that hydrogen off relatively easily, leaving it with a lone pair of electrons that can then act as a nucleophile, right? So in all of these, this is my nucleophile. And of course, that carbonyl carbon is going to play a role of the electrophile, okay? So if it's just this aldol addition, right, we have this coming up. Whenever that carbonyl carbon is the electrophile, we get that tetrahedral intermediate, and we ask ourselves, is there a good leaving group? In the case of an aldehyde, you only have a hydrogen and a carbon, so there is no good leaving group. So instead, what we're left with is sort of this negative charge here that has nowhere to go. So the only thing we can do is cap it off with a hydrogen. Okay. The reason why I want to start here is, again, these are probably the three most important reactions with regard to this chapter. And I really want you guys to notice the patterns of the functional groups that we're producing. And in this case, it's a carbonyl group and an alcohol group located exactly 3 carbons away from one another. That's always what you're going to get with an aldol addition.
Are you missing a carbon product? Because there was one.
Oh yeah, you're right. There's one on this side. That, and then my hydrogen was back here, and that's the bad leaving group. Yeah, you're right. Nonetheless, the pattern of the functional groups, right, being 3 carbons away, that still holds. You're absolutely right. I did not account for this carbon over here, which is now pointed this way. Okay, so then what happens when I have heat?
We get a cleavage of the
elimination.
An elimination, yeah. So basically now this OH group is going to go off and become a double bond, right? So I'm going to have basically the very similar framework. Now this OH group that I had with just the as a leaving group, I've had an elimination reaction that leaves me with a double bond. Importantly, notice how that double bond is spaced perfectly so that it can be in resonance with this carbonyl group. Sorry, I didn't finish drawing. Right, it's not over on this other side here. It's located exactly so that it can be in resonance. And again, in terms of noticing patterns of my functional groups, I again have this carbonyl carbon and this double bond, again, located 3 carbons apart. Right, so in terms of just easily spotting, and a main reason to do this is because this also allows you, if you need to do the retrosynthesis, to figure out which bond has just been created. Remember, I told you to start numbering, right? So you're going to start numbering from that carbonyl carbon, 1, 2, 3. Could do the same thing down here, 1, 2, 3. And in terms of sort of the retrosynthetic point of view, that new bond is always going to be between carbons 2 and 3. Okay, so if you ever needed to work backwards. All right, so now down at the bottom with the Claisen, it's a little bit different because I have an ester, not an aldehyde. So what's going to happen with this group right here that I'm circling?
It's going to leave.
A leaving group? Oh.
Awesome. It's going to pop off. It's going to act as a leaving group. And so notice what that's going to do to the functional groups that I get in my product. Instead of having a carbonyl group and an alcohol group located 3 carbons away, I have 2 carbonyl groups located that same 3 carbons away. Okay, now I said that this was kind of a Claisen because this is actually a weird reaction where I first took my ketone, turned it into an enolate ion, and then reacted it with an ester. Remember, a traditional Claisen reaction would just be taking a sample of ester like this and adding some sort of base right? And now you're going to have two of these molecules reacting with one another. So everybody take a second and give me what the product of that would be.
Wait. 1, 2, 3, 4. 1, 2, 3, 4. Okay.
Okay, so basically I'm going to have now two molecules of this. One of them is going to be acting as the nucleophile, so I'm going to make this, whoops. This is going to be my enolate ion. I'll color it purple again because it's my nucleophile. The other molecule has the electrophile. So now we have something very similar, but the one side hasn't lost that ester group.
Yep.
All right, so one of my esters remained intact. The other one acted as a leaving group. I still have that pattern of two carbonyl groups located kind of in kissing distance, those 3 carbons away, but I also have an ester on one side. Okay, and then again, if I'm going to sort of like do the retrosynthesis problem, obviously I've already given you the reactants, so this isn't a hard one, but if we need to just look at the product and figure out where our new bond is, we're going to play that same numbering game, but we're going to start at the carbonyl carbon that has that ester. Okay, so then 1, 2, 3, and again, the new bond is located between carbons 2 and 3. Notice that no sort of elimination can take place from this step because I don't have an alcohol group at the end, I have that carbonyl group. Okay, let's do similar. I'm again going to take this same sort of enolate ion, but now I'm going to react it with this guy here. All right, so first of all, what is this guy called? It's got like a cool name and a big ugly name. All right, so it's an enone.
Alpha beta unsaturated.
Or alpha beta unsaturated. So an enone, right? Ene, because you got that double bond located right next to a carbonyl group, an one, a ketone. The other, which is actually kind of more common, is an alpha beta unsaturated ketone or aldehyde. What is so special about our enones? All right, I'll give you a hint. Just like every other carbonyl containing compound in the world, they have this electrophilic site here, the carbonyl carbon. Well, what's so special about an enone?
Have one at the 1/4 position.
They have a second one, right? So this guy all the way down here, and you can look in the lecture notes, it has everything to do with resonance, but the bottom line is an enone has 2 electrophilic sites. Okay, that's the big pain in the butt about enones, is some nucleophiles react with the one site, some nucleophiles react with the other site, and we need to know where that line is, okay? So for this particular one, everybody, we're gonna take a vote here, use the chat. Do you think it's going to react at electrophilic site 1 or electrophilic site 2? Everybody take a second and decide and put it in the group chat. All right, awesome. Good job, guys. So yes, this is going to be for what is just a normal old enolate ion, like this guy. It's going to react at the boring normal carbonyl carbon position. So because of that, just sort of, you know, I'm not going to do the whole mechanisms just because they take time, but sometimes showing you a piece of them gives you a clue as to what the functional group's going to be, which is the key part. And so here, this is going to attack that carbonyl carbon. What always happens when your carbonyl carbon gets attacked?
Pushes electrons up.
That pair of electrons has to jump up to that oxygen, right? Because carbon can't have 5 bonds. So that means at the end of the day, we're going to get an alcohol group, right? So first it's going to be kind of stuck. Stuck as that negative charge. But then of course, the only thing we can do there, because there's no good leaving group, is cap it off with a hydrogen. Notice that because of where it attacked, I still have, it's a little bit like kind of wonky and crooked because I got so many bonds going on. But I still have my 2 functional groups located 1, 2, 3 carbons away from one another. So this is basically just a normal aldol addition. That double bond portion, that ene portion of our enone didn't do anything for us. Right? It's still there, still surviving, all that good stuff. Okay. So this would be, you know, kind of the cheat sheet slide of what reacts at the other position. These are what we call our Michael's donors. Clearly, Michael was the dude that kind of came up with this reaction here. And so this would be the list. The big one, I think, to really keep in mind is this pattern here. When you have your enolate ion form at the very middle of 2 carbonyl groups, right? So again, you got 2 carbonyl groups located 3 carbons apart. If that carbon 2 is your enolate ion, yeah, that's going to be the biggest pattern to observe. If you remember, we kind of lumped nitriles in with there, and then this and this are kind of sitting on their own here. Okay, so file those away as sort of a special exception. But if I'm only going to remember one thing from this list, I'm going to remember this pattern here of those 2 carbonyl groups spaced 3 carbons apart. Okay. And so then everybody, let's take a second and do what the product of that reaction would be. Again, I have my whatchamajiggy, enolate ion. Okay, so here, my nucleophile, but now this is going to be my electrophile. All right, and so my new bond has been created between those two carbons. All right, so here's where counting carbons might be even more important because we don't have the same sort of like pattern of functional group that's going to pop out to us. Because actually all of our carbonyl groups has remained intact. What we've really done is sort of added to that double bond. So here, you know, doing sort of double checking your work. 1, 2, 3, 4, 1, 2, 3, 4. All right, cool. You know, count carbons in this compound. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm always counting carbons when I'm doing organic chemistry because it's the easiest way to make sure that you haven't made a mistake, right? Leaving out a carbon, like I did on the first example, because I wasn't doing a good enough job counting carbons. It's just something that's really easy to do. So a good way to double check that you haven't made a stupid mistake. Okay. All right. Last on this sort of same sort of deal here. What if I took what was originally my compound here that we said reacted at that 1, 2 position. I took my same enone, but now I really want it to react at that carbon there. What can I do? This isn't a Michael's donor, but there's still a method that we learned about that we can use in order to have it react at that 1,4 position.
Stork synthesis.
Yes, boom. This is the Stork enamine synthesis. That's the whole shtick about the Stork enamine synthesis is it takes what would be a strong nucleophile, a 1,2 adder, and converts it into a Michael's donor. That is what Stork synthesis does. It makes a ketone that would not otherwise be a Michael's donor into a Michael's donor. Okay, this was something that clearly was missed by just about everyone. And so make sure particular reaction, just to sort of show in the notes here. Very next slide here is the Stork enamine synthesis, where basically what you're going to do is take your ketone and you're going to react with a secondary enamine, and that guy is a Michael's donor. So again, this is just a method of taking any old ketone or aldehyde and converting it into a Michael's donor, so it's guaranteed to react at that 1,4 position. Cool. All right. So then what this is going to do is, so again, sort of just our list of reagents here. I'm going to take this in the presence of acid, and then I'm going to have to remove water as it's formed. That's how I'm going to sort of isolate my enamine. So really the hard part of this question, I think, would be, you know, what are the reagents that we put here? So like R2 and H in acid, get rid of water, and then we'll have it react where we want it to. Okay, and again, sort of just to be sure, 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3. Okay. One of the things, just so first of all, I hope everybody saw that I posted that announcement with like the ACS resources. They have like a practice test that you can pay $10 for or whatever. I mean, you're more than welcome to do it. There may be something you can find online. You guys are amazing at finding pirated crap online like that. The ACS is notoriously fantastic at taking down its copywritten information, but I'll put it past y'all. Nonetheless, the one thing about the ACS that I want to just kind of note, It has a lot of those problems that are kind of similar to what Wiley Plus does, where it does, there's a whole section on multi-step reactions. So what that's going to be is it's going to have one reagent and then a list of like one substrate and then a list of like 4 different reagents that do back-to-back-to-back reactions. And you're going to have to know what the products are. Okay, this is really where the first semester information is going to come into play. They're not going to be as concerned about the mechanisms that we learned in the first semester, but just in terms of knowing the general reactions from the first semester. Again, my advice would be go to those earlier chapters to the very end where they have those summary reaction wheels and study those summary reaction wheels, right? You guys learned all those reactions at one point, but it's been a hot minute since we've reviewed some of them. So just highly recommend you go back and sort of prep that way. You don't have to read through the whole chapter, but looking at a summary of those reactions will be important. Okay. On this chapter, just to sort of do some intramolecular stuff, what happens when I take our product here and then just toss it in some sodium hydroxide with heat?
You
This is
can
actually-
form a pentene.
So take it, yeah, everybody take a
Condensate.
second and draw me exactly what we think the
Crystallization.
product is. We're making sure that the spacing in the ring is the hard part, I think. This is where I saw most people trip up on the exam. Is it a 5-membered ring? Is it a 6-membered ring? How do we tell?
It's the number of carbons between the carbonyl groups.
Right.
No. So that is where everybody messes up. It's not the distance, the number of carbons between
The
these.
carbonyl to the alpha.
It's the carbonyl to the alpha, right? It's the distance between your electrophile and your nucleophile. And so that's where a lot of people made the mistake, is giving me, in this case, a 5-membered 1, 2, 3, 4, 5. It should be a 6-membered ring, because that's my alpha carbon that's going to be the nucleophile to my electrophile. But yeah, nonetheless, everybody take a second and give me what the product of this reaction would be. But yeah, common mistake. Okay, and so then how I do these sort of cyclization reactions, just to make sure that I got everything straight, because oftentimes you're going from something that's linear into something that should be cyclic, is to actually just start with, you know, the shape of what your cyclic compound will be, and then decorate it accordingly. So in this case, because I know it's going to be a 6-membered ring, I'm just going to start with a hexagon. You can even go as far as like sort of numbering these guys. And then I need to make sure to decorate all these carbons with what they should have based on this, right? So carbon 5, I'm going to need that carbonyl group. Sort of, and you know, you could have looked at it two different ways. I'm going to say that this is my nucleophile and carbon 1 is my electrophile. So that means that carbon 1, not only should I have this methyl group sticking off of it, I should also have an OH group, except for the fact that I said that there was heat. So instead of just sticking around as an OH group, what's going to happen?
There's going to be a double bond.
There's going to be a double bond. So I'm going to have the elimination after that as well, right? So in this case, where is my double bond going to be located? Means carbons what and what?
1 and 6.
1 and 6, yep. And again, this is just where noticing those patterns really helps. Remember, what's the most important thing about that double bond after the elimination? It's in resonance with that carbonyl group, right? So again, I have the perfect spacing such that I have my newly formed double bond in resonance with my carbonyl group. Okay. Cool. Another thing that the ACS exam loves are these thermodynamic versus kinetic synthesis problems, right? So the effect on temperature when I just have, sort of the same set of reagents. So in this case, the difference here is I'm going to have high temps, base, and then, I don't know, some alkyl halide. This is going to be low temps, base, and that same alkyl halide. What are the differences between these two reactions? Again, the ACS just loves these thermodynamic versus kinetic type reactions. There's a few that I think there's maybe only two. Anyways, this is one of the ones that we learned. Actually, the other one was from the first unit, so we'll review that in the next hour. But nonetheless, these are kind of often seen as well.
The high temp will be the less sterically hindered, and the low temp will be the more stable.
The antithetical.
Other way.
Yeah.
Dang it.
Right. So the way to think about it is low temps, things are moving slowly. So
So
less
it's
steric
faster.
hindrance means you have more chance of contact.
Now with the high temp one, would it like throw you for a loop if it creates a chiral center?
No. Well, I mean, it could, you maybe should know that it's going to be a racemic mixture. It's not going to have any stereospecificity. So I could see them throwing you a question where they were like, is it the R enantiomer? You know, sometimes they like to say, is the product this? And they give you the nomenclature for it instead of the actual structure.
Is it not just an SN2 reaction? Like one is tempo.
R enantiomer and the other one being a racemic mixture. What's up?
Will it not just be an SN2 reaction with the, or maybe not?
No, it is. I guess you're right. So if I had this being stereospecific, that could be something that that would not necessarily produce a racemic mixture. As drawn, though, this is kind of already showing you, right? When you don't specify a stereochemistry, you're assuming that it's a racemic mixture.
Okay.
But yeah, you're right. It is going to be just a simple SN2. Okay, so the big difference here is which hydrogen gets removed, right? It's actually the first step, the creation of that enolate ion, that's going to be different for each one of these conditions, whether it's this guy back here or one of these guys over here, right? So this blue one or this orange one. And again, low temperatures always means kinetic, the kinetic product, the one that forms the fastest. Okay, and that's all about which one of these hydrogens is going to be the easiest to grab, right? Because again, at low temperatures, things are moving really slowly. So, you know, which one is going to be less sterically hindered? In this case, the enolate ion that we're forming is going to be over on that carbon. Remove the blue hydrogen. That one's the more accessible one. High temperatures are thermodynamic. So what's more stable? And in this case, that's going to be removing the more highly substituted hydrogens. So now we have our enolate ion over here. Okay, so in terms of the difference between what we get at high and low temperatures, notice it's the alpha carbon in both of these cases, right? Alpha carbon chemistry chapter. But going to be where that new carbon-carbon bond is formed. Okay. For this particular one, I just said base. It turns out that in practice, use different bases at low temperatures would be LDA. At
Sodium
high
hydroxide.
temperatures, your base is sodium hydride. Yeah, I mean, something to keep in mind, but I don't know that that would be what I would be looking for as much as the temperature and the thermodynamic versus kinetic control. Especially if they're asking you like to which one of these best explains why this reaction happens this way kind of deal, right? You just want to have a sense of what it means to be kinetic versus thermodynamic. The sort of picture, I guess, to maybe have in your mind, how they illustrate it.
Like free energy diagrams.
Perfect, yeah, exactly. Is this free energy diagram here? All right, so kinetic, which happens faster. Again, because this carbon is less sterically hindered, the fastest one is going to be the formation of this kinetic enolate ion. All right, so removing it from this purple one here. In terms of thermodynamic, that's how you have what's more stable. Then you're looking at this half of the graph, right? So it's all the way on the product side, and the fact that this one is at a lower free energy is why that one's better. Okay. And just looking at these two enolate ions, why is this one, the more highly substituted one, the more thermodynamically stable?
The more highly substituted double bond, the more stable.
More highly substituted alkene, right? So remember, you know, there's got this negative charge on the oxygen. That's actually not what's important. It's the location of that double bond, how it's more highly substituted position. So alkene stability business is something that's going to come up again and again. Okay.
So for the last step of these, they form a double bond.
So remember that this is the lazy man's way of drawing an enolate ion. And it's preferable because then when you're drawing mechanisms, you can just go straight from your nucleophilic carbon to your electrophilic carbon, all that good jazz, right? But when we talk about an enolate ion, we're always talking about a structure that's in resonance. So if I was being really good, I wouldn't just draw that one, you know, something like this. I would draw it in resonance with this guy here. And that's really where the name comes from, enolate. Right? Think about if we're just going to break this down, enolates. The ene corresponds to the double bond. The olate is, you know, like a carboxylate where you have the negative charge on the oxygen. So we always, just because we're lazy and it's easier to sort of draw mechanisms with and all that jazz, we tend to sort of focus on this as being our enolate ion. Remember, things in resonance, it's not that it's switching back and forth, it's that both are true at the same time. So if we're being really good, every time we drew an enolate ion, we would actually draw both of these structures here.
Okay.
That's a good question. So it's not unusual to see for, like, just in this particular example, people using this structure here, and then their resonance or their reaction mechanism would have this double bond going and attacking there at the same time as that oxygen comes down there. That'd be a perfectly reasonable reaction mechanism involving an enolate ion. Again, you can just kind of save yourself an arrow if you draw that structure there. All right, this would get kicked off, being lazy with my mechanisms here. Okay, just before let's do a few from the other chapter here. right, so how do we convert between these carboxylic acid derivatives?
Is it NH3? I thought it was NH. Is it NH3 or 2?
It's 2. Draw these a little better. All right, so for the most part, remember that the way that these are stacked are from most reactive to least reactive. Okay. You can also think of reactive as stability, right? So the most unstable, i.e. going to be the one that's going to want to react the most, is that acyl chloride. The least reactive or the most stable is going to be that amine. Okay? For the most part, when you're going from something more reactive to something less reactive, it's pretty straightforward in terms of what you need. You're just going to look at what sort of functional groups are you needing to swap out, right? So if I'm going to go for an acyl chloride to what do we call this guy?
An acid anhydride.
An acid anhydride. I'm going to just take whatever is in that orange box, and that's what I'm going to mix in, right? So in this case, it would be this carboxylate ion is the key there. When we're using acyl chlorides, though, we also need to include what?
Something to
Oh wait, no,
balance out the chlorine. So like
Is it
pyridine.
pyridine?
It's pyridine, yeah. So it's really a base so that you don't have a buildup of HCl that occurs. Okay, so basically if you were to do this, it's so reactive that what's going to happen is you're going to produce hydrochloric acid, which is actually sort of a gas, or can be a gas, and then you get all this toxic whatever. It's not that the reaction won't work, it's that you'll poison the whole room if you don't have some base in there that's going to help mop up that acidic hydrogen. So the go-to is pyridine, and that goes for most all of these ones here. Can't go wrong to just throw in some pyridine. So again, I'm going to just put in whatever's in that orange box. You actually, certainly if you used sodium ethanoate or something like that, it would work. But there's no need to use something more expensive. You could just use methanol. An alcohol is more than reactive enough with an acyl chloride to get you, what do we call these? Esters, yep. same thing with
For the
if I wanted a carboxylic acid, I could use sodium hydroxide. That would work, but so would just straight up water. Okay. There is a little bit of a difference when we're making our amide. I'll give you a hint. We don't have to use pyridine for some reason.
Is it just gonna be the NH3 or excess NH3?
Exactly, yeah. So basically, you're going to have one molecule of NH3 acting as your nucleophile, and the other molecule is going to act as the base, right? So instead of having pyridine in there, we would just have 2x of the NH3.
For the first one, going from the acyl chloride to the acid anhydride, you can also make that a alcohol instead of the enolate, right?
No, well, that's not what we learned. Because the reason is, well, first of all, if you had this here, that would react with your pyridine, and so you would just create the carboxylate. However, I think the better way to think about it is it has to do with sort of the gap. When I'm going from an acyl chloride to an ester, that's a huge jump from most reactive to less reactive, right? The jump is not as strong here. So what we learned is that you need a carboxylate ion. You need like sodium carboxylate to react with your acyl chloride. However, if you had an excess of pyridine, again, that would just act as a base. So, yeah. Okay. So what if I want to jump from an acid anhydride to a ester?
You're gonna be the ROH.
Yeah, which is what's an ROH?
Which is pretty much alcohol.
Alcohol. Yeah, exactly. Right. So again, just like we did before, all I would need was methanol. That would react with an acid anhydride. If I'm going to go from an ester to an amide, what do I need to do?
It'll just be the NH3 alone.
Yep. So again, notice jumping from the less reactive to the more reactive is fairly straightforward. You're just going to look at the derivative portion that you're swapping out, and that gives you a clue as to what you need to do. The big exception is this one here. Why can't I just take my, in this case, acetic acid, throw in some ammonia, and get an amide out on the other side? This is not what happens. Why?
It's a good base, so it's going to pull off the hydrogen from the alcohol.
Yeah, exactly right. Don't forget all the way back from chapter 3. This is an acid. This is a base. So before any fancy nucleophilic acyl substitution reaction happens, you're just going to get an acid-base reaction. And the big problem is this. Carboxylate is not going to be an electrophile. And this ammonium ion is not going to be a nucleophile, right? That's what you would need for this reaction to occur. But because of the acid-base reaction that happens first, you don't get that.
So like, wouldn't you have to turn that into chlorine first? Wouldn't you have to react it with SOCl2?
Yeah, so the standard way to do it is to actually first take us back to this acyl chloride group. Okay, because this is actually, one of the only ways we know how to jump back to an acyl chloride is from a carboxylic acid, and that is using, so first, SOCl2. And again, all that does is jump us back to the acyl chloride. So then from there, I can do what I did down here and add 2x of ammonia.
Could we also turn that carboxylic acid into an ester and then the ester into the amide?
You can, but in practice, you wouldn't, because both of those reactions don't go to completion as much. So you're always going to have like some equilibrium distribution of products. But yes, for pencil and paper organic chemistry, you're absolutely right. You could. There's nothing kind of illegal about that. If you're in the lab, you're performing two sort of inefficient reactions, one after the other. Basically, I mean, the bottom line is this heat reaction here does take place, but it's really slow and it's not 100% efficient. So yeah, so what you'll see in practice is what's here.
Okay.
Okay. You know, I want to make sure to stick to time here. The one other thing that I would say that's like super crucial for this chapter, like a standard takeaway. You saw we did this reaction in lab a trillion times, even with our very limited lab kit sort of whatevers, is the Fischer Esterification, right? So going from either a carboxylic acid to an ester or vice versa under acidic conditions. This is something where I would make sure to know the mechanism both ways. It's just something that's considered like a staple in second semester organic chemistry 2. Know that not only that reaction happens, but make sure you know the mechanism. I could just see them asking, is this an intermediate in this sort of reaction kind of deal, right? I mean, even though it's a multiple choice, they will still ask you some reaction mechanism questions in the form of like, does this intermediate form as part of this mechanism? You know, is this step where they're drawing arrows, what happens in this reaction, right? So if we focused on mechanisms in class, it's not because I'm trying to be a huge pain in the butt. It's because I can foresee them asking a question very mechanism driven on the ACS. Okay, so any questions about this before we jump to Unit 1 stuff? So first of all, if you're here for your credit for the makeup exam, you're all good. You can hang around for the Unit 1 review. I highly recommend you do. You get like that 2-point extra assignment going on if you do stick around. If you decide not to stick around, it's not going to harm your ability to take the makeup though. Okay, but before we move on, does anybody have any questions about Unit 3 material?
I did have one question. We went back to the Stork and we used the sodium hydroxide with the heat. Why was it a 6-membered ring and not a 5-membered ring?
It was a 6-membered ring and not a 5-membered ring, because what you're counting is not the spacing between the two carbonyl groups, right? So this is what I think the #1 mistake made on the exam was people went 1, 2, 3, 4, 5. I should have a 5-membered ring. But these two carbonyl carbons are not forming a new bond with one another, right? They're both electrophiles. So the real spacing that matters is the distance between your electrophile, which is going to be one of these carbonyl carbons, but the nucleophile is going to be an alpha carbon. So that's either this carbon here or this carbon here. So you're either going to get a 4-membered ring that forms or a 6-membered ring that forms. And remember, we don't really like forming 4-membered rings.
Yeah, it's 5 and 6.
So in this case, it's going to be a 6-membered ring that's formed.
Okay. And it's 5-membered and 6-membered favored, right?
Correct, yeah.
Okay. I'm sorry for
in all of organic chemistry, pentagons and hexagons, right? There's a reason why we don't know how to draw stuff more complicated than that.
All right.
So are we allowed to talk about like the exam 3 makeup or not?
Yeah.
Yeah, so I had a question on that, which was number 10 with respect to this one.
Okay. The actual take-home portion?
Yeah, are we allowed to go over that or not?
Yeah, sure.
Yeah, okay. So I had a question on number 10. That's the one I couldn't figure out. It was from the Claisen condensation.
Okay, let me make sure I know what number 10 is.
I also have the same question. Yes, I couldn't figure it out either.
Cool.
I mean, it was just, I didn't even know what to do on that one. I kind of just guessed on it, but I'm pretty sure I got it wrong. I didn't do it right.
Yeah.
So that is this big ugly thing. And again, well, let me actually draw it just exactly the same as I had it
Just
here.
because what confused me is that oxygen right there on by the carbonyl oxygen. That's I couldn't figure out that part.
Oh, it forms a 5-membered ring. Huh?
Oh, wait, okay, wait. Let's do this one first. And then this goes down to this. So this was a perfect example of me being, wow, that was terrible. Hold on, I gotta fix that. Of me being tricky just by giving you something big and ugly, but it's really not anything crazy going on here. Again, what are we gonna do in order to find out where that new bond is formed?
It's gonna be to count 3 carbons away.
It's gonna be count 3 carbons away. Where do I start?
Well, they start from the
Yeah.
carbon, part of the oxygen's at.
Yeah, so I'm gonna start with the one with the intact ester group. 1, 2, 3. And so where's my new bond?
Between 2 and 3.
2 and
Between
3.
2 and 3. So right off the bat, I can kind of pick out what my nucleophile is gonna be.
It's a crossed out or Claisen condensation.
It's definitely a cross Claisen condensation. So this would be my nucleophile. What's my electrophile going to be? I got a portion
Aldehyde?
here, not an aldehyde.
No.
Because if it was an aldehyde, what would be my final functional group? I wouldn't
Oh,
have.
it would be stuck to the alpha carbon here on the.
No, but I wouldn't have these 2 carbonyl groups located 1 and 3 apart. I would have a carbonyl and a what? If it was an aldehyde.
It's gonna be an ester.
It would be a
alcohol group.
carbonyl and an alcohol if this was a Claisen. But the fact that I have 2 carbonyl groups means exactly right. I got to have some ester over here. Doesn't matter what it is because it acted as a leaving group.
Oh, so what I did is that I put that same ester on that one right there. Would that still be okay or not?
This R can be anything you want it to be.
Oh, then I guess I did it right then. So because I just drew a 6-membered ring around that.
Well, I mean, the
I'm
only
not sure
problem with
that's-
that would be you can't have 3 bonds on your oxygen. So it can't be this.
Oh, yeah, that's what I did because I kind of
Yeah,
thought it
well,
was.
now your oxygen has 3 bonds, right? So that would be the only illegal thing there. But the bottom line, I mean, what I was really trying to get you guys to understand with this problem is this pattern of the fact that you have 2 carbonyl groups located 3 carbons apart. There had to have been an ester leaving group form, or in order to form that particular compound.
That's where I got confused about that. Like I wasn't sure like if it had to be an ester or, but I just. But I got that first part right where you jumped down right there.
Yeah, cool. Well, make sure you know it for the exam, right? That's the important part.
I mean,
Again, just going back to the very beginning. Hold on, Bryce. We'll definitely get to you in a second. Just going back to the very beginning, sort of recognizing pattern kind of stuff going on here, right? This is kind of, if there's one thing you're going to remember from this chapter and you're going to scrap everything else, being able to pick out these patterns are crucial. All right, what's up, Bryce?
So I got stuck on the same question, but like I got to the part you have there, but I couldn't figure out what the ester group would be. So it can be anything?
Can be anything.
Okay.
I mean, the way that this reaction would have had to have worked is I would have taken this guy first, added LDA to it, and then slowly titrated that in.
Makes sense.
Okay. Typically, if you have, what am I trying to say? Like in a typical Claisen reaction, you have just some sample of ester reacting with itself. And then in that case, the important thing is to make sure that whatever base you're using
Yeah, the same.
has the same back end as that ester.
Yeah.
But I can always do these reactions in 2 steps where I take it, titrate in LDA, make sure I get my enolate ion, and then titrate in the other one. That's also legal.
Okay.
The bottom part was what again?
This
Yeah.
is like a normal Claisen
Oh, normal place.
condensation, where you just take some, I got my liquid isopentyl acetate, right? Like we created the banana oil. If I took that and titrated base in, it would end up reacting with itself, forming a Claisen condensation.
quick
But
here, another question.
for the
Regarding
pKa
the-
stuff, what's it on slide 13 of chapter 20?
Slide, it's chapter 21 is going to be the Claisen. Is that what we're talking about?
For the place, and I was saying for like the pKa information, was that slide chapter 20, 13?
I have no idea. Chapter 20, slide 13. I don't know. Well, what do you mean the pKa information?
Well,
this stuff?
we started the exam with like ranked pKa's of the following things, and I remembered it had something to do with like electron withdrawing, electron donating, and I wrote on my test reviewed slide 13, but I wasn't sure. Yeah.
Yeah, I mean, I guess 13 is going to be this one. So slide 12, I think, would be, if you're
Yeah.
talking about chapter 20, it'd be slide 12, which is going to be for all these different benzoic acid derivatives. The bottom line is if it's a electron withdrawing group on there, it makes a stronger acid because you stabilize that carboxylate group. If it's electron donating, you're destabilizing that carboxylate ion, making it a worse acid.
Thank you.
Cool. All right, let's move on to, let me just stop and restart here.